In this module, you'll be introduced to a workflow designed for combining geophysics and targeted conventional sampling to characterize landfills. This workflow was developed during the Rawfill project and has been tested on a range of different landfill sites. Within the Rawfill project, geophysics sits between DST1 and DST2 as means of gathering more information on landfills of interest. Results of a well-designed geophysical survey should yield the information required to enable Orion to make an accurate assessment of the potential uses of these landfills in question. Orion being the second decision support tool as explained in the second module of this course. But first, what does geophysics mean? Geophysics is a field within geology, which is comprised of a range of non-invasive methods specifically designed to characterize the subsurface in terms of geological structures, groundwater, contamination, and/or human artifacts. These methods use lateral and vertical mapping imaging of physical properties of the subsurface. In our case, landfills can be seen as human artifacts. Why do we want to use geophysics for characterizing landfills? Here is a quick explanation. The conventional approach consists of drilling boreholes and sampling at specific depths. This provides accurate point information, but little information in terms of spatial characterization. The large quantity of point samples needed can incur at a significant cost. Furthermore, the invasiveness of the process can lead to increased risks of leakage or cross-contamination within different landfill bodies, between the landfill and the groundwater system, or directly at the surface. With this in mind, the Rawfill project has developed a workflow combining geophysical methods and conventional sampling techniques. The workflow is based on two principles. Firstly, it is necessary to combine as much multiple geophysical methods as possible in a complementary way and apply this to case-dependent problems. Here is a quick example showing this complementary approach with a geoelectrical survey. The methods mentioned will be later explained in the video. Applying geoelectrical methods on a landfill site is effectively injecting an electrical current and measuring the resulting voltage along a range of electrodes. With these methods, we measure the electrical resistivity, but also the chargeability of the subsurface. Comparing these two complementary parameters can already improve the interpretation. By repeating the injection of electrical currents over different electrodes, the mapping of the subsurface's resistivity is compiled. For example, in this model, areas of low resistivity in blue could be interpreted as zones of increased moisture content, clay content, or metal content. But one can also get a chargeability model of the subsurface by applying the induced polarization method. With this additional information, areas with low resistivity and high chargeability can now be narrowed down to being zones of increased metal content. Together, these two methods deliver data that can be interpreted with an increased certainty. The second principle of the Rawfill workflow concerns the targeted sampling, where geophysical methods reveal the extent of waste or zones of interest within the waste. Targeted sampling provides tangible information on the composition of such zones. The results of targeted sampling are used to calibrate and validate the assumptions drawn from the geophysical results. It is called targeted sampling because the geophysical results are used to guide the sampling, with the aim of minimizing the number of samples needed with respect to a conventional landfill characterization approach. The main benefits of using targeted sampling are the cost savings, a reduction of the risk of damaging landfill structures, and a reduced risk of contamination or exposure to hazardous materials. In a nutshell, geophysics is non to minimally invasive, has a relatively low cost and provides large spatial coverage at high resolution. On the other hand, it only provides indirect information, which needs to be processed, modeled, and interpreted by qualified geophysicists. Often the spatial resolution decreases with depth or with distance to the measuring device. The need for data processing and modeling also makes geophysical methods prone to modeling errors, also called artifacts. In conclusion, geophysics is most powerful when combined with complementary methods and interpreted together with all the additional information available from a specific site. Now let's have a look at the workflow developed through the Rawfill project on how to use both geophysics and targeted sampling at a given site. It is composed of 4 steps. First, the archives and inventory reports. This step consists of gathering and summarizing all available information for the site. This step aims to build a first conceptual ground model, but also to assess the knowledge gaps and chart what the knowns and unknowns of the site are. Second, the geophysical characterization itself. The first conceptual ground model is used to plan a geophysical campaign using relevant complementary geophysical methods to address the knowledge gaps. The main goal is to image the geophysical properties in the subsurface. Third, targeted sampling. A sampling plan is developed based on the results of the geophysical report, like identified zones of interest, the lateral and vertical extent of the waste, and so on. The main goal of this step is to tie the geophysical signature of specific zones in the landfill to physical measurements in order to calibrate, validate, and refine the original ground model. Step 2 and 3 can be done repeatedly. Fourth step, the resource distribution model. Combining all of the collected information of the previous 3 steps, the model of the landfill is subdivided in waste bodies based on the refined conceptual ground model. This provides detailed information about location, quantity, and type of wastes in the landfill. The resource distribution model can either be conceptual or spatialized in 2D or 3D, depending on the level of information gathered in the first 3 steps. Now let's illustrate this workflow with a synthetic case study. Here is an ordinary landfill site. At first glance, there are potentially a lot of unknowns. What type of waste has been buried in the landfill? What is its volume, or how far does it spread? What type of cover material, if any, was used and how thick is it? Are there any contamination issues? These are typical knowledge gaps for a landfill site. First step of the workflow, gathering and summarizing all the available information. Various sources may need to be tapped to acquire whatever data is available. Some typical sources are historical reports coming either from the site owner or the local authorities, aerial photography archives, previous investigation reports, and permits. A site visit is also vital, as it is the opportunity to discuss the knowns and the unknowns of the site with the people in charge. A lot of practical information is sometimes not available in reports. All these pieces of information are gathered to build the initial conceptual model and to assess the knowledge gaps that need to be filled by the geophysical campaign. After gathering all the information, a better picture of the landfill at the surface is attained, allowing the planning of the geophysical campaign. But also, all these pieces of information help building the initial conceptual model of the subsurface of the landfill. In this example, we were working with a model with 2 types of waste surrounded by bedrock and natural soil. Once this first conceptual model is built, we can switch to the second step, the geophysical characterization. The main goal of this step is to fill the knowledge gaps as much as possible. In this case, we mainly need to confirm the lateral and vertical extents for each type of waste and cover layer. We also need to confirm that there are two types of waste. In order to do so, the geophysical campaign is designed to first apply mapping techniques. Electromagnetic induction, EMI, and magnetometry, MAG, are two powerful mapping techniques. Electromagnetic induction measures the electrical conductivity variations in the ground at specific depths. Magnetometry maps the local magnetic anomalies. These rapid mapping techniques give a quick overview of the subsurface of the site with a good spatial coverage. It is sometimes not possible to map the site completely due to the topography, vegetation, or objects which prevent passage or generate anomalies in the measuring signal. This can be the case with metallic objects such as cables or fences, which disturb electromagnetic or magnetic devices. After these rapid mapping techniques, some profiling methods can be applied. These methods provide images with higher resolution at depth. They can result in 2D profiles or 3D models, depending on the measurement strategies. In this example, we show the combination of electrical resistivity tomography and induction polarity techniques on 2D profiles, in which each waste type has a specific resistivity and chargeability signature, while the topsoil and the bedrock have other distinct signatures. The images also suggest that there is a cover layer on top of the waste. In the Rawfill project, we have tested a broad range of geophysical methods, which each measure useful information depending on the characteristics of a given site. Electrical resistivity tomography is usually relevant when looking at cover layer thickness, waste zonation, leachate content, groundwater table, or geological structures. Induced polarization brings information for characterizing the cover layer thickness, the vertical extent of the waste, and the waste zonation within the landfill. Ground penetrating radar is useful in most cases to detect utilities or assess the cover layer thickness. Electromagnetic induction and magnetometry allow to quickly map the lateral extent of the waste, utilities, and potentially identify zonation within the waste. Finally, seismic methods mostly inform on the vertical extent of the waste and the geological structures. This table illustrates the importance of applying an integrated approach using complementary geophysical methods and which are based on a priori information. After the geophysical characterization comes a third step of the workflow, targeted sampling, with the aim of validating and calibrating the geophysical results. A limited amount of boreholes, trial pits or trenches, target specific locations in the landfill. Here, 6 boreholes have been chosen to cross-validate the extent of the two waste types, which have been already updated from the geophysical campaign. In this example, a cover layer has been identified with the electrical resistivity tomography on top of waste type 1, which is an important information to have for building a sampling plan. Here is an example on how to create a sampling plan based on the interpretation of all the geophysical results. The electromagnetic induction map shows us several anomalies. It is usually good to target areas with high conductivity anomalies as they can highlight an increase in metal, organic or leachate content. Then also some of those with low conductivity, which represent the background image or zones with more inert materials. Results from other methods indicate additional zones of interest. For example, in the electrical resistivity tomography image, we identified conductive anomalies at depth. Because the decrease of resolution with depth, the actual depth of these anomalies need to be calibrated, while their origin need to be determined. Note that in this case, the electromagnetic induction map is also useful to avoid buried pipes in the drilling process. After the targeted sampling, the ground truth data is compared and cross-correlated with the geophysical results in order to classify the geophysical images into a certain amount of waste types. This process feeds into the final conceptual model of the site, which can now be called a resource distribution model, RDM. The RDM provides information in the form of waste types, distribution, and quantity, which are crucial for the assessment of feasibility for a landfill mining project by Orion, the decision support tool. This decision tree chart summarizes why and when to use geophysics to characterize a landfill. In summary, using geophysics is cost-effective as it allows targeted sampling and it delivers data with a relatively high spatial resolution in a non-invasive manner. The workflow developed in the Rawfill project advocates the collection of available information, applying a combined set of complementary geophysical methods, enabling targeted sampling to build a resource distribution model. The result of this approach aims to provide ready-to-use information for decision support tools and decision makers. Let's start with magnetometry. As you know, the Earth produces its own magnetic field and behaves like a magnet with a positive and a negative pole. In the image, we can see the schematic representation of the magnetic field lines and how they change their orientation as they get closer to the poles. This is only a schematic representation because in reality the magnetic field lines look more like this. Mathematical models, however, together with real observed data from satellites, observatories, marine and terrestrial surveys, allow us to have a good knowledge of the magnetic field behavior. Depending on the position on Earth, different magnitudes and orientations of the magnetic field will be measured. For example, in the city of Liège in Belgium, the Earth's magnetic field has an inclination of 66 degrees with respect to the Earth's surface and a magnitude of 48.87 nanoteslas. The magnometry method aims to find disturbances in the Earth's magnetic field caused by buried magnetic objects or structures. Data acquisition is straightforward. An operator moves through the area he wants to cover. If there are buried magnetic objects, an anomaly with respect to the Earth's magnetic field will be observed. These anomalies originate from contrasts in magnetic susceptibilities in the subsurface. The data can be interpreted in two ways. First, they can be interpolated and, for example, displayed on top of an aerial view of the site investigated. This qualitative approach allows to locate anomalous zones. The second approach, more quantitative, consists in modeling the data but requires prior knowledge of the site. For example, in the image to the right, the observed magnetic anomaly can be reproduced by a model composed of several layers with different magnetic susceptibilities values. However, in landfills, what modeling may reveal might be quite complex given the high heterogeneity of the waste generally observed. As an example, the following site investigated in Rawfill used to be a municipal solid waste landfill located along the coast. In the image, we can see the blue and red anomalous values of the magnetic field induced by the waste deposits. In this case, magnometry revealed useful to delineate the lateral extent of the waste. These are the pros and cons to this method. For example, it is well suited to detect large magnetic objects or to delineate areas with higher metal content within the waste. But on the other hand, infrastructure of the site, such as metal fences, pipes, or excavators, can interfere with the measurements. Also, given the heterogeneity of the waste generally observed in landfills, a quantitative interpretation of the data may be non-trivial. Next, we will discuss the electromagnetic induction or EMI method in the frequency domain. The acquisition system is composed of several antennas or coils. One of the coils is used to transmit an electromagnetic wave in the subsurface. The resulting magnetic field, called the primary field, will induce currents in the subsoil whose intensity depends on the electrical conductivity of the soil. These currents will in turn create a secondary magnetic field. Both the primary and secondary magnetic fields can be detected with one or more coils called the receivers. By making a few assumptions, the imaginary part of the ratio between the secondary and the primary magnetic fields can be associated to the apparent electrical conductivity of the subsurface, and the real part of the same ratio to its magnetic susceptibility. There are different coil orientations that affect the sensitivity and depth of investigation. Among the most used, one can cite the horizontal coplanar array, where both transmitter and receiver are laid in a horizontal plane, the vertical coplanar configuration, where both coils are in the vertical plane, and the perpendicular coplanar configuration, where the transmitter is in the horizontal plane and the receiver is perpendicular to it. In general, the horizontal coplanar configuration is more sensitive at larger depth than the vertical coplanar configuration. In addition to coil orientation, there is an important parameter related to the depth of investigation, the skin depth, delta. The skin depth is defined as the depth at which the amplitude of an incident, or originally transmitted, electromagnetic wave has decreased of about 37% compared to the initial amplitude. As we can see in the formula, the skin depth is inversely proportional to the frequency of the transmitted wave and to the conductivity of the subsurface. In other words, this means that the depth of the investigation decreases with the conductivity of the subsurface increases. Another important parameter is the induction number, beta, which is proportional to the distance between the transmitter and receiver coils. All the sensors work under the assumption of low induction number, beta being much smaller than 1. It is under this assumption that the received signal can be transformed into electrical conductivity and magnetic susceptibility. We also see that the skin depth is proportional to the distance between the transmitter and receiver coils. But at the same time, the distance is limited to maintain the assumption of a low induction number. In any way, there are some rules of thumb that we can use to have an idea of the depth of exploration of the device we're using. For example, for a horizontal coplanar configuration, the depth of exploration is about 1.5 times the distance between the transmitter and the receiver coils. The owner's site, for example, is a former limestone quarry where slag lime, fly ash, and other industrial waste were deposited. Electromagnetic induction was a very suitable tool to delineate the lateral extension of the lime and ash, as both materials are characterized by large electrical conductivity, displayed in blue, compared to the limestone bedrock and other materials present on the site. To sum up, there are pros and cons to the method. For example, it proves to be useful to delineate the lateral extent of the waste and detect areas with increased leakage and/or metallic scrap content, but on the other hand, this method is limited in depth, which is further reduced in highly conductive media. The following chapter is an introduction to electrical resistivity tomography and induced polarization. Both are commonly used in near-surface geophysics. Let's discuss the basic principles of each method. Both methods are designed to determine electrical properties of the subsurface and can usually be measured with the same machine. Electrical resistivity tomography, ERT for short, and time domain induced polarization, TDIP or induced polarization for short, aim to determine respectively the electrical resistivity and chargeability distributions of the subsurface. The higher the resistivity, the more difficult the current can flow through the material. Electrical resistivity is the inverse of electrical conductivity. Electrical resistivity tomography is generally used to provide information on pore fluid, porosity, and lithology. Induced polarization quantifies rather the ability of a soil to store electrical energy, also called chargeability. It is generally used to detect clays, metallic objects, and organic contaminations. Since chargeability is sensitive to pore shape and size, it can also be used to estimate soil hydraulic properties. The setup used in the field to collect electrical resistivity tomography and time domain induced polarization measurements is the same. It consists in planting a series of electrodes, generally made of stainless steel, in the ground, either along a profile to obtain a 2D image of electrical properties or along a grid to obtain a 3D image. The electrodes are then connected on multi-core cables, and these cables are then connected to a resistivity meter, an imaging system containing preloaded sequences for automated data acquisition. The acquisition begins by injecting an electrical current of a given intensity at a pair of electrodes, A and B. The resulting difference of voltage, delta V, is measured across two other electrodes, M and N. The configuration shown is known as Venner alpha, but other electrode configurations are possible. Taking into account Ohm's law, the ratio between the difference of electrical voltage at M and N and the injected current at A and B gives an electrical resistance. Measuring the electrical resistance is the basis of the electrical resistivity tomography acquisition. Time domain induced polarization measurements consist in measuring the residual voltage after the applied current has been switched off. Due to polarization effect, this voltage is non-null and decays with time. A measure of the induced polarization effect consists in calculating the ratio between the voltages just after the current is switched off and just before it. This ratio is known as chargeability and is generally expressed in millivolt per volt. However, due to technical constraints, it is very difficult to measure the residual voltage just after current cutoff. Therefore, an alternative way to measure the induced polarization effect consists of measuring the voltage decay at discrete time intervals. The integral of these values divided by the voltage just before current cutoff and the integration time gives the apparent chargeability, also expressed in millivolt per volt. Once the electrical resistance and chargeability have been measured for a given quadrupole, the acquisition continues with the neighboring electrodes in order to study the lateral variations of electrical properties. Then the spacing between the injection and potential electrodes is increased to explore deeper horizons. The acquisition continues until the combinations of the given configuration have been completed. In the end, the dataset may contain hundreds or even thousands of measurements. Data processing, together with the mathematical process known as inversion used to convert electrical resistance and apparent chargeability to electrical resistivity, as well as true chargeability, will not be discussed here. Instead, we look directly at the results of the inversion. The displayed resistivity model shows three horizontal layers with contrasting electrical resistivity properties. At the surface, we observe a homogeneous layer with medium resistivity that overlays a less resistive one. At the bottom of the model, higher electrical resistivity is present, which is typical of unfractured bedrock. Note the loss of resolution in the bottom part and on the edges of the model. This is inherent to any surface geophysical methods and can be explained by the lower data density in these zones. Looking at the chargeability model, the interpretation can be refined. Layers 1 and 2 are likely composed of different materials. Given the chargeability and resistivity values observed, the second layer probably has a higher clay content. When planning a survey or interpreting the results, it is important to keep in mind the limitations of the methods. For example, like all surface geophysical methods, electrical resistivity tomography and induced polarization suffer from loss of resolution with depth. In addition, the quality of the data has a strong influence on the models obtained. It is therefore important to ensure good data quality by choosing, for example, the appropriate acquisition parameters. It is also essential to quantify the quality of the data by repeating the acquisition several times or by collecting reciprocal measurements. At the end of the inversion process, image appraisal tools such as the depth of investigation index or the resolution matrix should be applied to provide information about the reliability of models. In general, it is strongly recommended that pre-investigation design, feasibility and appraisal studies are carried out before going into the field. Several tools exist to test different survey conditions and configurations using synthetic models. Now that we've seen the basic principles of how to carry out an electrical survey, we can look at a real application of the methods on a landfill. Case study presented is a former landfill characterized as part of the Rawfill project. The site was used for the deposition of municipal and industrial waste from 1962 to 1997. The following figure shows a cross-section of the landfill with the different filing stages. The geophysical investigations were mainly focused on the northeastern part of the landfill, where the thickness of the waste is estimated to 11 to 12 meters and where no liner is present. We present here an electrical resistivity tomography and induced polarization profile conducted in that zone. See the green line. The acquisition settings are shown in the blue box. The three figures represent respectively, from top to bottom, the electrical resistivity, the chargeability, and sensitivity models. The resistivity model shows several layers with contrasted properties. At the soil surface, a more resistive layer in red is observed, which can be attributed to the unsaturated part of the cover layer made of sand and inert material. Underneath, we observe a thin layer, less resistive, on top of a more resistive one. The less resistive layer probably corresponds to the part of the cover material containing more water. The layer below is likely less porous and less permeable, hence the observed resistivity. Beneath this layer, there is a very conductive zone in blue, probably related to a high leachate content. The chargeability model mainly shows two zones. The top zone, characterized by very low chargeability, can be attributed to the cover material. The bottom zone, exhibiting high chargeability, can be related to the municipal solid waste. The high chargeability of municipal solid waste can be explained by the presence of metal scraps, plastic sheets, and organic matter. Trial pits conducted along the profile validated the provided interpretation. A borehole conducted along the profile revealed that the bottom of the landfill was at an elevation of 17.5 meters. Clearly, the sensitivity or the resolution of the model at that depth is not sufficient to image correctly this interface. After this brief introduction to the electrical resistivity tomography and induced polarization methods, it is time to summarize how they can be used to landfill investigations and to highlight their advantages and disadvantages. Both methods are among the most useful for landfill characterization, as illustrated in the following table. Electrical resistivity tomography and induced polarization are particularly suitable for imaging the cover layer thickness and the waste zonation. Given the expected high chargeability of municipal solid waste, induced polarization provides a means of estimating vertical extent of such deposits when their thickness does not exceed the depth of investigation of the method. Because of its sensitivity to fluid content and associated properties, electrical resistivity tomography is very suited to detect and study leachate present in landfill. In terms of acquisition, both methods require a limited number of staff. Since induced polarization involves measuring the voltage decay after the injection of current, acquisition takes longer than electrical resistivity tomography. Although data processing can be automated, the inversion process requires expertise and may be time-consuming. Electrical resistivity tomography is a simple and robust method. In addition, the targeted property offers a high variability ranging from less than 1 ohm meter for pure conductor to millions of ohm meter for hydrocarbon-containing rocks. Due to the large spatial coverage it offers and its limited cost, it is generally cost-effective. Furthermore, since it is sensitive to fluid content and composition, it is an ideal method for monitoring fluid dynamics in the subsurface, such as, for example, leachate injection. On the other hand, the geoelectrical problem is underdetermined, thus the solutions obtained after inversion are non-unique. The inversion problem itself is very complex and requires a great deal of expertise. Finally, an overlap between different materials may exist. For example, household waste containing leachate may have the same resistivity value as clay. Induced polarization measurements can provide very useful information in the search for disseminated minerals. The method is particularly sensitive to clay and metal particles and offers the possibility to quantify them. The disadvantages of induced polarization are the same as those of electrical resistivity tomography. In addition, not all the electrochemical phenomena underlying the induced polarization response are fully understood. Finally, induced polarization surveys are slower and therefore more costly than electrical resistivity tomography surveys. With the following presentation, we introduce the main concepts and principles of seismic methods applied to landfill characterization. There are different types of seismic methods, which can be divided into active and passive methods. In this presentation, we're going to introduce MASW, which is the acronym for Multi-Channel Analysis of Surface Waves, and SRT, which is Seismic Refraction Tomography for the active methods, and Horizontal to Vertical Noise Spectral Ratio Technique, in short called H/V, for the passive methods. As explained in the introductory presentation, seismic methods are part of the profiling methods, meaning they are used to obtain a 2D slice or even 3D image of the landfill material below the measured profile lines. In comparison to other geophysical methods, especially active seismic methods require more staff for the field survey and more time for the processing, but they can be very successful in providing detailed information about vertical extent, compositional waste zonation, and changes in the geology below the landfill. Passive seismic methods, whose main strength is the determination of the vertical landfill extent, require less staff and processing time. However, its interpretation requires calibration with other methods or ground truth data. Seismic methods study the propagation of seismic waves. In particular, they look at the propagation velocity of these waves. Seismic waves are pulses of strain energy that propagate in solids and partially in fluids. They are generated at a source, which can be a natural source, such as an earthquake, or an artificial, such as a hammer blow. They can also be active, such as a hammer blow, or passive, such as the vibrations generated by ocean waves. The energy released by the impact of the source is transmitted by tiny particle vibrations through the subsurface, and these small ground motions can be recorded at a seismometer or geophone. This registered record is called a seismogram. The velocity at which the seismic wave travels is determined by the physical properties of the media through which they travel. The relevant properties are ground stiffness, elasticity, and density. There are two different types of seismic waves, which are called body waves and surface waves. Body waves, which can be further split into pressure and shear waves, travel through the bulk of a medium, and surface waves travel along the surface. The different wave types travel at different velocities and have different amplitudes, here illustrated with this seismogram, which was registered after an earthquake. The P waves are the fastest and arrive first at the seismometer, followed by the S waves and by the surface waves. The surface waves are the slowest, but they have the highest amplitude. Another important property of the surface waves is that they are dispersive, meaning that different frequency components travel at different velocities. As an example, this table shows the velocities of pressure waves from different types of material. We can see that the velocities for solid rock with high bulk density are faster than for unconsolidated material such as clays and sand. Landfills are on the slow end of the graph. This is due to the often low compaction of landfill material. Poor fluid saturation of unconsolidated materials has a strong influence. The velocity of saturated sand is significantly higher than the one of unsaturated sand. However, different seismic wave types have different velocity characteristics. Apart from being slower as we've seen before, shear waves, for example, do not travel in fluids and therefore don't change velocity in the groundwater table. In addition, shear waves and surface waves are more sensitive to changes in ground stiffness than P waves. The goal of seismic methods is to create a subsurface model of seismic velocities. Interpreting material-specific velocities, specific materials can be assigned to the different measurements in a model. For an active seismic survey, the general setup includes several geophones which are aligned along the surface and a source, such as a hammer, to trigger seismic waves. The different active seismic methods look at different wave types and different propagation paths. Refraction seismics look at body waves, which are critically refracted at interfaces with a strong contrast, and multi-channel analysis of surface waves looks at the surface waves whose propagation is bound to the ground surface. The processing steps of the two methods are quite different, yielding similar looking results despite returning different types of velocity. These images show example results of a seismic refraction survey on top and an MASW survey at the bottom. Both surveys were measured over a landfill, yielding a clear pattern with the waste material having low velocities in blue and the bedrock with clearly faster velocities in red. The top image is given as P-wave velocities and the lower image as S-wave velocities. The data processing for an active seismic method is quite complicated and requires experience. Very simplified, there are three main steps. First, assigning of geometry to the field records. Second, picking either first arrivals for SRT or the dispersion curves for MASW. And third, deriving the final velocity profile through an iterative inversion process. If you're interested in more details about the processing, you can download additional information in the references provided below. Now, we briefly describe the principle and data acquisition of a passive source seismic method called horizontal to vertical spectral ratio of noise, abbreviated as HVSRN or simply H on V. By recording the seismic ambient noise, this method aims to estimate the dominant frequency induced by local layering of stratigraphy. Compared to other seismic methods, the equipment is simple and easy to set up. A seismometer is placed on the soil surface and connected to a data logger. Then the ambient noise vibrations within the soil are recorded for a certain duration in three directions, 2 in the horizontal plane and 1 in the vertical direction. After selecting the most stationary noise windows and additional processing, the ratio between the Fourier amplitude spectra of the horizontal to vertical components of the ambient noise can be calculated and plotted as a curve in function of frequency. The resonance frequency appears as a peak whose amplitude depends on the impedance contrast with the underlying layer and whose frequency depends on the thickness of the surface layer. However, as shown in the formula on the right, to estimate the thickness of the surface layer, its shear wave velocity must be known a priori. As for all geophysical methods, there are challenges. A significant issue is high noise levels in the recorded signal. For seismic methods, especially rain, wind, or moving vehicles or persons during the recording can produce noise. A certain noise level is always present and is not a problem as long as the signal is still clearly detectable. However, as soon as the noise grows to a similar range as a signal, the signal gets masked and consistent processing becomes difficult to impossible. Therefore, it is very important that a seismic survey is planned properly in advance so that potential noise sources can be limited to the minimum. Other important factors to consider are the resolution and depth of investigation. For example, for seismic refraction, a good ray coverage, as indicated in the lower right figure in black, is important. Therefore, an adequate survey design with reasonable geophone and shot position spacing is important. Similarly, the layout of the geophone array will define the possible depth of investigation, which can be estimated to be about 1/5 to 1/10 of the profile length. Important points for MASW are: the geophone spacing defines the minimal detectable layer thickness. Therefore, the closer the geophones, the thinner layers can be detected. The depth of investigation of an MASW is shallower than for SRT. On landfills, this is often about 15 meters. Thus, in short, seismic surveys need to be designed in accordance with the required depth coverage and expected subsurface heterogeneities. Seismic methods are very powerful tools to gain detailed information about vertical extent, compositional waste zonation, and changes in the geology below the landfill. The seismic refraction is the main method to delineate the vertical waste extent for up to greater depths. However, the main limitation is the hidden layer problem, meaning that a layer of lower seismic velocity underlying a layer of higher velocity cannot be detected and might cause ambiguity in the interpretation. The MASW, in contrast, is able to detect such hidden layers and is therefore a potential powerful method to delineate different waste zonations. However, the main limitation is the limited depth of investigation. H/V can be a very efficient tool to detect the waste thickness. Next, the basic operation and application of ground-penetrating radar will be reviewed. GPR. GPR is a geophysical survey tool that can be used to detect changes in material or to locate point/linear features such as buried utilities. GPR is a very shallow investigative technique, generally limited to the upper 10 meters of the subsurface. Consequently, the use of GPR on landfill assets is limited in terms of depth, but can be particularly useful in mapping the thickness of landfill capping layers, for example. Most modern GPR systems can be operated by a single person and the data collected can be visually interpreted on the fly. Example given for the location/avoidance of buried obstructions. All the data can be recorded and subsequently post-processed for detailed/numerical analysis and interpretation. Although GPR data can be collected very quickly and cheaply, the time and hence cost required to process and interpret the data can be much greater compared to the cost of the data acquisition. As the name suggests, GPR uses radar. Radio wave signals penetrate ground materials and are reflected, scattered at interfaces between materials of contrasting electrical properties. This phenomenon was recognized during the 1950s when US Air Force realized that repeated crash landings on ice fields were due to reflections from the base of the ice being misread as reflections from the surface. In concept, GPR operates in a manner analogous to seismic reflection. An electromagnetic radio pulse is transmitted downwards into the ground, where it then propagates until it meets an interface between materials with contrasting properties. Some of the energy will be reflected back to the surface to be recorded by a receiver along with the travel time taken. Some energy may also be scattered by point features, such as buried service lines, for example. The properties that control the transmission/return of a radio signal are the dielectric permittivity of a material, which determines how fast the radio signal travels through the material, and the electrical conductivity, or how well a material conducts an electric current. Often the inverse of conductivity, electrical resistivity, is measured in the field, and this is shown in the table here. In many soil and rock materials, it is the water content that's one of the major factors in controlling the permittivity. GPR systems transmit a short burst of sinusoidal radio waves, which contain a range of frequencies around the central dominant frequency, by which a GPR antenna is classified. A GPR signal will lose energy during each cycle or oscillation as it propagates. Signals with shorter wavelengths will become more attenuated per meter traveled than signals with longer wavelengths, and therefore the maximum depth of investigation will be reduced. The choice of antenna frequency, therefore, has a significant effect on the depth of investigation. As the propagation of radio energy causes an electrical current to flow within a material, proportionally much larger currents are stimulated in more electrically conductive materials and therefore more energy is lost or attenuated through transmission. For this reason, GPR is often not particularly effective when used over particularly conductive, fine-grained clay soils or in areas where salt water are present. Conversely, GPR performs exceptionally well when surveying over dry sands, ice, or even through fresh water. For a signal discontinuity to be resolved, the wavelength of the signal must be smaller than the distance separating one interface from the next. Where the thickness of a layer is less than the wavelength of a GPR signal, some interference of the reflected signal from the top and bottom interfaces will occur. When a higher frequency antenna is used, in this case an 800 MHz antenna, it can be seen that each of the interfaces are resolved unambiguously. This means that the frequency of antenna chosen for a survey will have a significant effect on the level of vertical resolution that can be achieved, and a balance must be struck between the level of resolution and depth of investigation required. The next few slides will illustrate how GPR data are collected in a mapping type application as may be deployed over a landfill asset. GPR is commonly deployed as a pair of transceivers, transmitter TX and receiver RX, separated by a fixed distance common offset, which are then moved across the survey area, usually over a regular geolocated grid or with a GPS antenna to provide locational information. Often individual radio wave pulses will be triggered by an odometer wheel at constant time intervals, particularly when GPS information is co-collected, or can be manually triggered by the operator at desired intervals. An EM pulse is emitted from the transmitter, producing a repeatable signal characteristic of the antenna. Note that every GPR antenna, even if nominally the same frequency, will have a slightly different response and therefore will produce slightly different signals. The signal propagates through the subsurface until it reaches a discontinuity in dielectric properties, where part of the signal will be reflected back up to the receiver. A part of the source radio wave will continue propagating into the next layer, where it may be reflected at a subsequent interface. At each measurement location, a signal trace will be recorded, showing peaks and troughs where energy has been detected by the receiver. A single GPR trace is very hard to make sense of, but by arranging the traces in the order they were collected along a profile, it becomes clearer to see what type of feature the radio wave signal has been returned from. Typically, the energy is returned from layers which form continuous but often irregular surfaces, or it is returned from discrete point features where the return energy is diffracted and forms a hyperbolic distribution, the peak of which will be centered on the feature itself, as shown in the image above. In summary, GPR operates by transmitting pulses of electromagnetic waves into the ground, through which they propagate until they are reflected or diffracted at discontinuities in dielectric properties, with any returned energy detected by receiver antenna. EM waves are attenuated by the ground, with the amount of attenuation controlled by the electrical conductivity of the ground. The more conductive, the greater the attenuation, which affects each oscillation of the EM wave. Resolution is a function of wavelength proportional to 1 over the frequency, with higher frequencies resolving smaller or more closely spaced features. The trade-off being that higher frequency signals will be attenuated over much shorter distances and therefore useful for shallower depths than lower frequency signals. To demonstrate where GPR has been successfully applied to in the study of a landfill, an example of a 250 MHz GPR survey undertaken at the Les Champs-Jouyaux landfill in Normandy, northern France, as part of the Rawfill project is presented. The objective was to try and determine the thickness of cover materials above the waste, but also to detect any pipes or infrastructure located within these layers. A very clear interface, red dotted line, is observed across the entire area, interpreted to be the top of the drainage layer, due to the presence of buried pipes, indicated in orange, just below. Given the depth of this layer was known from construction records at the site, it was possible to estimate thickness of the rest of the GPR section. A second, semi-continuous layer, yellow dotted line, was observed at a depth of about 2 meters, which was interpreted to correspond to the top of the waste itself. Picking these two surfaces across the entire area of the GPR survey meant that it was possible to construct maps of the depth to these two interfaces across the survey area, isosurfaces. Although no information regarding the composition of the waste itself was obtained during GPR, the information regarding the thickness of the capping/cover layers is extremely useful in characterizing the overall landfill structure and can be used to correct data gathered using other geophysical techniques for the presence of the materials overlying the waste. Additionally, in cases where the feasibility of landfill mining needs to be assessed, knowledge of the thickness of the capping layers or cover allows for accurate cost estimations for excavation or to determine potential volumes of reusable materials to be made. When using GPR in the study of landfill deposits, the relatively high speed at which data may be acquired means that GPR can be deployed as a rapid tool to map large areas of landfill. This can provide information regarding the thickness of capping or cover layers and therefore increase the existing knowledge of a landfill deposit. The effectiveness of any survey, however, will be limited by the presence of conductive materials such as salt water or particularly fine-grained soils.